had studied in
Students.
that lecture and how we are proceeding further. So one topic which we covered in the
झाला
last
त्या
lecture
गळती
was
सुरू झाली.
current transport phenomena in
काय 8 दिवस
semiconductors
झालं राहिलं.
and PN junction diodes. We studied the
तिकीट बुक केलं का?
drift phenomena, diffusion phenomena. We also studied the thermal current transport at thermal equilibrium condition in the PN junction diodes. We also studied the role of Hall effect in identifying the carrier concentration and the carrier type,
पुस्तकं पटकन.
and then heterojunctions. And you know that when we discuss LEDs, we could find that heterojunctions play a big role in making the modern electronic devices, or you can say in improving the already existing optoelectronic devices or photonic devices like photodiodes, LEDs, lasers, because of the structure
हे
of the
निघालं होतं.
hetero junction
साप निघाला होता मला
structures,
भीतीच
we are
वाटायला
able
तेव्हापासून.
to
लॅबमध्ये
get
पाऊल
very
टाकायचं म्हणलं की भीतीच
efficient
वाटायला.
devices. So let me move further. That is the laser diode. So this I am discussing. You can see this picture. This is the structure of a laser diode. We all know the laser, and what happens, what kind of physics is associated with the laser, that is important to understand. By definition, the semiconductor diode laser, also known as injection laser diode, is a semiconductor that produces what? That produces coherent radiation or stimulated radiation in the infrared region and in the visible region of the EM spectrum. So it uses PN junction to create radiation with the same frequency and phase. So you can see here you have a bottom contact, then there is a substrate, then there is a cladding, then diode, then again cladding, and then top contacts, and this phase from where the beam of light emerges out of diode. So let's study its structure. So semiconductor diodes in which emitted radiation produces a monochromatic and highly directional, which means coherent light, beam of light, is known as laser. Semiconductor laser is has a length of 100 micrometer and is easily modulated at higher frequencies by modulating the biasing circuit. By modulating the biasing circuit, we can take it to a very high frequency. Means you can have a beam of very high frequency laser beam using semiconductors. So then there is a structure. See energy band diagram. If you look at this energy band diagram, and if you have seen the energy band diagram of PN junction diode, you should be able to note the difference. I hope you must have noted, because there is a P-type region and there is an N-type region. You know that what happens, you have a conduction band H, there is a valence band H, and we always say the Fermi level lies between the valence band and the conduction band. But here you see the Fermi level is below the valence band in P-type, and if you look at N, there also you are not finding Fermi level within the forbidden band. It is above the conduction band. So this kind of semiconductor is somewhat different what you see in normal PN junction diodes. So see that what is written here, degenerate semiconductors. So in order to understand this, we first understand degenerate semiconductors. I had already touched degenerate semiconductors, if you remember, while discussing the doping concentration, P-type, N-type. I stated about one situation that where what happens, where the you say that number of electrons in the N-type material due to doping, number of dopants in the N-type material are more than the density of states in the conduction in N-type material, and number of holes, number of electrons in N-type and number of holes in P-type are more than the density of states in the valence band. So I told in that situation, these are known as degenerate semiconductors. I think at least we should pick up the concept of degenerate semiconductors. It's very important. It is useful in many very, you can say that very efficient applications. So degenerate semiconductors are the semiconductors in which doping levels on the N side as well as on the P side, means both sides of the PN junction are high enough so that the Fermi level are below the valence band H on the P side and above the conduction band H on the N side. So this is what I told you earlier also, that the concentration of electrons in the N side is more than the density of states in the conduction band, and concentration of holes on the P side is more than the density of states in the valence band, or in otherwise, or in other way, you can say that doping levels on both sides of the junction are high enough so that the Fermi levels are below the valence band H on the P side and above the conduction band H on the N side. To enhance stimulated emission, you know that stimulated emission is the prerequisite term associated with lasers. Stimulated means have same wavelength, multiple particles possess multiple photons possess same wavelength and same phase also. To enhance the stimulated emission for laser, we need population inversion. Another term which we use, population inversion, means number of particles or charge carriers in the excited state are higher than the number of charge carriers in the ground state. You know, normally what we say in the ground state you have more charge carriers than the charge carriers in the excited state, but in laser we want more number of charge carriers in the excited state, so this term is known as population inversion. To achieve the population inversion, in a semiconductor laser, we shall consider PN junction formed between degenerate. If you have PN junction which is formed by degenerate semiconductors, your number of charge carriers in the versus if you see this figure shows the band diagram of degenerate semiconductors. That's okay. And if you forward degenerate semiconductors, so situation will be like this. So if the band will be reduced and your level is goes higher, more closer to the energy level of the conduction band. So So when forward biasing is applied, electrons are injected from N side and holes are injected from the P side, as shown in figure B. When large forward bias is applied, C, as you will see, high injection occurs, large concentration of electrons and holes into the transition region. So there will be high concentration of electrons and holes in the injection. See here, it has gone above EC level also. First it was much below than the lowest EC level. When you applied forward bind, this kept on reducing, and a stage came when this is even higher to conduction band here and higher to valence band on the other side. So when the this is under large forward. When large forward bias is applied, high injection occurs, large concentration of holes and electrons are injected into this transition region is a depletion region, which is denoted by small d here. So there is more population, more concentration of electrons and holes in the transition region when you apply high forward bias. The transition region, which is denoted by D in figure C, contains large concentration of holes in the valence band and large concentration of electrons in the conduction band. This condition is known as population inversion. Condition for population inversion persists till EFC minus EFP is greater than band gap. EFC minus EFP is more than EG. If this condition prevails, this is mathematical condition for population inversion in a PN junction. So this is the concept of population inversion. So another aspects about the laser, that how it makes carrier confinement or how it makes optical confinement. So see this A and B. A is showing you PN gallium arsenide PN junction, and B is showing you double heterojunction laser. Means here aluminium gallium arsenide, which is also known as L gas, then gas, then L gas. So there are two junctions of gallium arsenide with aluminium gallium arsenide. So this is one heterojunction, other is also heterojunction. So this is known as DH laser, double heterojunction laser. This is PN homojunction laser or PN homojunction diode. Here we can say PN DH laser. PN double heterojunction diode or PN double heterojunction laser. Structure is same. The figure A shows the schematic representation of band diagram of PN junction under forward bias. So this is under forward bias, which you see here. Condition, while figure B represents double heterojunction structure for the laser. So this I already told you. This figure also shows the refractive index. See this one and this one. This shows us refractive index profile, and next one below that, this is optical field distribution of light generated at the homojunction laser and double heterojunction laser. So when light generates here, then what is the scenario with respect to the refractive index, and what is the scenario for light control? I hope I am audible.
Yes, sir.
Thank you.
Thank you.
Thank you.
Yes, sir.
figure also shows the see, this is the refractive index. In case of PN homojunction, you see that in the transition region, there is a slight higher value of refractive index than the refractive index value of the P-type region, P-type neutral region and N-type neutral region. So in the transition region, in the depletion region, the refractive index value is slightly higher in case of PN homojunction lasers. Whereas in PN DH lasers, in the transition region, you see this refractive index value is quite high, 5% high means, and transition region here quite wide 2 micrometer, here it is 0.5 micrometer. So whereas in DH laser the width is low, whereas the step is high in DH laser in comparison to homojunction laser. And if you see, the figure also shows the refractive index profile and optical field distribution of light generated at homojunction laser and DH laser. So this is the light generation profile. See that you read from here, the carriers are confined in the active region. It is almost completely confined within the active region by heterojunction barriers, the two barriers, they confine the carriers. While in homojunction, the carriers can move away from this transition region outside that, in the neutral, up to the neutral region, where recombination may also take place. If recombination takes place in the neutral region, so this won't help us in the intensity of beam with that emerges. That means that is a wastage. So you say that wastage is quite high in homojunction for these carriers, whereas in DH lasers is almost utilized for our purpose. The optical field is strictly confined within the active region by abrupt reduction of refractive index in the DH laser. So that is the reduction, refractive index reduction is able to confine the charge carriers over there. So see this, let's see the light optical confinement, carrier and optical confinement. The optical confinement can be explained in the figure shown here, which shows you can see 3 layers. Inactive region, N1 bar, N1 is indicating the refractive index. Active region, N2 bar, inactive region, N3 bar. So you can say that layer 1, layer 2, layer 3. Layer 1 is N-type L gas, layer 3 is P-type L gas, layer 2 is gallium arsenide. So the optical confinement can be explained in the figure shown opposite, which shows 3 layers dielectric waveguide with refractive index N1, N2 and N3. An active layer is sandwiched between the two confining layers, and N2, the refractive index of active layer, is higher than one inactive layer and the other inactive layer. So this is higher than that. What will happen? This I am talking about the DH laser. The refractive index in the active layer is larger than the surrounding layers. The propagation of EM radiation is guided in the direction parallel to the layer interfaces. So you can see that radiation is guided, total internal reflection takes place, and radiation is guided by these parallel planes emerged due to the interface of inactive layer L gas with gas layers on both the ends. So the propagation of EM wave radiation is guided by in the direction parallel to the layer interfaces. No confinement factor, optical confinement factor. which is another ratio of the light intensity within the active layer to sum of the light intensity within active as well as outside the active layer. So this is the expression for confinement factor. This depends upon delta n, which is the difference in the refractive index, and thickness of the active layer. So if you know the difference in the refractive index, and if you know the thickness of the active layer, you can calculate, there is a constant, you can calculate the confinement. So this is how laser, semiconductor laser has various aspects as far as their design, their optical and carrier confinement, refractive index, etc. So let's see that how it is available in the laboratory and how it is available in the market. PN junction figure 1 shows a P gallium arsenide and gallium arsenide metal contact top and contact here. So pair of parallel planes are cleaved or polished perpendicular to 110 axis, which we ensure that radiation should come out of this axis, and remaining sides are often to eliminate movement in other direction. So light should not move in other direction, it should be coming out of these parallel planes 110 planes. And this particular structure is called fabricated cavity. The particular plane, two different planes are allocated for light confinement within their region. So under appropriate biasing conditions, radiations will be emitted from, you can see this radiation is emitting from 110. But if you go to B, this is a double heterostructure laser. A thin layer of gallium arsenide is sandwiched with layers of L gas, P-type and N-type. And C is a commercially available. What is available in the commercially? Metal, oxide, P, gallium arsenide, then L gas, then gas, then L gas, then. So it's a very protective structure which is available commercially. The laser can be fabricated using a technique known as epitaxial crystal growth. This laser requires much less current to operate than junction laser. This laser requires much less current to operate. So these are the three: homojunction laser, heterojunction laser, and commercially available. And this is how a laser which is available in the laboratory keeps its design. And these are the material. Normally we use 3-5 compound semiconductor solid solutions for obtaining stimulated emissions. These are aluminium, gallium arsenic, antimonite, gallium, indium, arsenic phosphate. So using this laser emission wavelength cover 0.3 to 30 and applications, light source, optical fiber communication, we use laser. For video recording and optical reading, we use laser. High speed printing, we use laser. After that, there is another device that is a photoconductor. Photoconductor, device whose resistance has function of light So when the fabrication photoconductors are fabricated, you take a insulator, you deposit semiconductor on them, and to the two ends of the semiconductor you make metallization, means ohmic contacts, are used to make the metallic leads. Photoconductors are fabricated by depositing film of semiconductor material on insulating substrate. It's not seen here. And metallic leads are attached to each end of the semiconductor. So cadmium sulfide, cadmium selenide, and cadmium selenides are among those which materials which are used as photoconductors. The photoconductor diode. So photodiode is subjected to photodiode is subjected to diode, PN junction diode, of course. And we also say it's a intensity detector. Means it can detect what is the intensity of the light that falls on it. Photodiode it works in the reverse biasing. Photodiode is subjected to photons in the form of light. That affects the generation of electron-hole pairs. So, if you take a diode and you apply reverse bias, you have differential region. In the P-type, you will have negative ions. In the N side, you will have positive ions. And if light is made to fall on this depletion region, additional electron-hole pairs will be generated. Right? No, photodiode is subjected to photon in the form of light, which affects the generation of electron-hole pairs. If the energy of falling photons is greater than the energy band gap of the semiconductor materials, electron-hole pairs are created near the depletion region of the diode, and electric current flow in the external circuit. What happens? This P-type, they are negative ions, and this here you have positive ions. If more electron-hole pairs are generated, holes will be pushed in this direction, electrons will be pushed in this direction, holes will be pushed in this direction, and electrons will be pushed in this direction. Now what will happen? When there is a battery and current positive from the hole side to the electron side, so it will flow in direction in the reverse bias. It will add to the leakage current. So suppose you don't shine any light, you may have curved reverse biasing characteristics, very low current. And when you shine light, it will be like this. If you shine more high intensity lights, it will be like this. The intensity keeps on increasing, response keeps on increasing. So what is this? This means that this is a detector of the intensity of light falling on this photodiode. Another aspects of the photodiode is this. If you are using high frequency light, or if photodiode absorb high frequency light, for high frequency operation, high frequency light detection, we can say, with must be kept thin from the time should be short, so that it can collect it within a very short span of time if you are using high frequency photodiode. On the other hand, the depletion width is increased or if diffusion bit is sufficiently thick, quantum efficiency will be more of the photodiode. So, on the other hand, to increase the quantum efficiency, the depletion layer width must be sufficiently thick to allow large fraction of incident light to be absorbed. Therefore, in practical photodiode, there is a trade-off between response speed and quantum efficiency. If your application is related to the high frequency particles, then you would like to have big depletion region. And if you want more quantum efficiency and you can compromise with the frequency aspects, you will use such photodiodes which possess large depletion region. So therefore, in practical photodiode, the trade-off between the response speed and quantum efficiency is the pitch of this level. Photodiode are available in the following types: insulated layer, P-type layer, insulated layer, N-type layer photodiode, metal semiconductor, short barrier photodiode, heterojunction photodiode, and avalanche photodiode. Five or four different types of that is the which is my research area also, and why I that, but anyhow, I want to talk about it. So we talk a lot about the solar energy production program, not in our country only, but all over the world. And most of you must already be aware that what are the different focuses. Number one, it is focused on the part of the solution to both Earth's energy and environment. To meet the energy demands of the world, as well as to deal with the environmental issues which other type of fuel is creating, which is creating a great threat to this human civilization. So the second focus is affordable energy for energy consumption. We don't want energy only, we want cheaper energy. That is also very, because for economically weak nations, if they have to use, it should be economically viable. The third one, lightweight flexible energy on the move. The third one is the lightweight flexible energy on the move. Means you should have solar cells which are lightweight, which are flexible, as you can see in this picture, so that it is easy to carry, to transport. Whenever you are walking, you are moving on a train or plane, and this is happening. Energy is continuously on production. So, what is the principle of involved in the photovoltaic solar cells? Photovoltaic effect, which is known as photovoltaic effect. So, light-induced excitation. If you throw light on a material and there is excitation to higher energy states, when the particles go to the higher energy states, excited states, it transports into external load without recombination. If this phenomena takes place, this is known photovoltaic. Means you shine light, particles are excited, and before recombining they go to the external load and helps in the flow of the electric current. If this principle phenomena takes place, we call it a photovoltaic conversion. Photovoltaic is a example of direct conversion of optical energy into electrical energy. And if you have to deal with the solar cells, you should know about the energy obtained or available from the sun. Number one, there are three kinds of spectrum which are very popular: AM0 spectrum, AM1 spectrum, and AM1.5 spectrum. AM0 means if you are outside the atmosphere, the this black line, and this is the wavelength, the x-axis, spectral radiance, kilowatt per meter square. So this is on the y-axis. So this line, this type of intensity energy is available. And if you are 1.5, that is not given here. This is average terrestrial. This average value is 1 is AM1. The terrestrial sun at zenith, when sun is exactly at your top, and whatever energy you obtain, that is known as AM1 spectrum. AM1.5 is the average terrestrial. So AM0 gives you 135.3 watts per centimeter square. AM1 gives 100 watts per centimeter square, and AM1.5 gives you 83.2 watts per centimeter square. So this is the different spectrum available for, because why people refer outside atmosphere also. You know that when you launch satellites, all energy requirements are met from the solar only. So you need to have a very efficient solar cell that is functional in the above the Earth's atmosphere. Then on Earth we are already using, and here also two types of spectrum, when sun is very high and other one is the average. And moreover, if you analyze solar energy spectrum, you will find that here ultraviolet 2%, visible light 47%, and infrared 51%. Although the intensity of the visible light is the highest. Intensity is the highest in the visible light. But if you classify the spectrum in terms of ultraviolet, visible, and infrared, so classification is like this: 2.5 micrometer, right from 0.38 to 2.5 micrometer. Micrometer is the spread, wavelength spread. Now, what are the various challenges of the solar energy? So there is a atmospheric attenuation seen in the solar energy. Means, scattering is seen in the Earth's atmosphere. Delay scattering is also there, a different type of scattering which is also there. And scattering due to interaction of light with molecules in the Earth's atmosphere, which is very effective, very, you can say, is most effective if your light having short wavelengths is involved. Means, if for short wavelengths the scattering due to molecules in the Earth's atmosphere is very drastic, And scattering by dust particles or aerosols is also there. Absorption by oxygen, ozone, carbon dioxide and water vapors present in the atmosphere is also there. Besides these 5 types of attenuations, there is another complication that when you have scattered light and you have a direct light and they intermix, the direct versus diffuse is 10 to 20% on a cloudless day, and this phenomena is higher if there are clouds, right? And moreover, if you have to understand the solar cell, how you should proceed. Solar cell is a junction with sunlight shining on it, right? In order to understand the working of the solar cell, we need to understand how a PN junction works, that we have seen also. And what happens if light is absorbed in a semiconductor, that also we have studied a little bit. And what happens when these two effects occur simultaneously. So, absorption of light and functioning of a PN junction diode simultaneously is affects the solar processing of the solar cells. You can say that working, functioning of the solar cell. Now, if you go to the different generations of solar cells, so basically it has been classified into 3 generations. Number 1, wafer based, means you have a semiconductor wafer, you have a monocrystalline silicon, you have a polycrystalline silicon, you have multi-junction cells, different band gap materials. Second generation, thin films, amorphous, monocrystalline, polycrystalline thin films of silicon, gallium arsenide, so this thin film solar cells. Another technology, cadmium telluride, thin film solar cells, copper, indium, gallium, selenium solar cells. Then low cost and high efficiency category. There is another category of solar cells which is known as low cost and high efficiency solar cell category. This is one, dye sensitized solar cells, quantum dot sensitized solar cells, organic photovoltaics, quantum dot polymer hybrid solar cells, perovskite solar cells, tandem solar cells. So different types of semiconductors make different kinds of solar cells for different applications. See the flaxy one, this perovskite one, see this wafer based, so everything is there. And if you see this scenario, types of solar cells and their efficiency. So amorphous silicon is 10.2%, monocrystalline silicon is better than that, 26.8. This is so far. And polycrystalline 29.1, polycrystalline 3.5, gallium arsenide 29.1, thin film chalcopyrides 23.35, perovskites 25.2%, organic cells 15.2. These are the thin film solar cells. Now, again, different semiconductors make different kinds of solar cells with different characteristics. I have already told silicon, single polycrystalline amorphous, gallium arsenide, CIGS, cadmium telluride, organic materials, perovskites also. These are some of the materials which are being studied extensively in the designing of the solar cell. And what type of structures we use? We use PN homojunctions or PIN. P insulator and N-type material homojunctions. PN and PN heterojunctions also. Metal semiconductor Schottky and MIS junctions, electrochemical junctions. Then what are the stability problems? There is a problem due to interdiffusion, which we have already talked. corrosion in the terrestrial cells means we use for commercial purposes or for the general purpose. So corrosion phenomena in those cells is a challenge. In its is a challenge for their stability. Particle bombardment damage in space cells. So those are used in the space applications. So particles bombardment to their structure is one such threat to the stability. Now I'll show you one. See, uh, can you see this slide?
Yes, sir. Yes, sir.
This is a interactive. This is an interactive table of solar efficiency for the different types of solar cells which are being studied. You see this here. You see CIGS. You see perovskites. Let me settle. Okay. So see which one has the highest efficiency. Highest efficiency is 47.6. 3,5 compound 3,5 multi-junction cells. Concentrator means we use the concentrator for focusing the light. Then we use the 3,5 multi-junction. So 47.6 has been achieved. And if I go to this one, this also 3,5 multi-junction cells without concentrated concentration. Here efficiency is 39.46. That is the maximum achieved. Year is also mentioned here. Then if you see 3,5, so 3,5 now perovskites is giving us. It's difficult to show. Perovskites efficiency 34.6, and this is CIGS. So like that. So if you can see this chart and you can find what are the various types of materials. These are absorber layers which are being used as absorber layers. And what is the status? This chart is updated 6 monthly by an REL organization. If you are interested, you can have a look at it and can uh, and can know the status, right? So this is what is basic solar cell. Now I'll talk one thing which will give you an interesting perspective about the solar cells. So it is also PN junction. You have already studied PN junction. And see here, it's a large area PN junction with solar radiation as input. Large area you see. So as you see that rear metal material, then P-type layer. On P-type, there is an N-type layer, and then this is a PN junction, right? And on that we put an anti-reflection film. On that we put this contacts. These are the contacts. These are, we also say grid. We also say fingers, like that. So PN junction is a large area PN junction with solar radiation as its input. We don't use any circuit. This is a standalone PN junction. Input is the solar radiation. The contact grid and anti-reflection coating are added to the solar cell, which is a PN junction, for efficient coupling of light into the device. So, average thickness of the solar cell is 3 micrometer, 0.3 micrometer, and thickness of the N-type layer is 0.002 millimeter, means 2 micrometer. So like that. And structure is, you have a substrate, then ohmic contact, there's the bottom P layer, top N layer, then junction is there, anti-reflection coating is there, transparent conducting oxide is there, and light is there. Now, maximizing light absorption and generation. Maximize the number of photons that get into the solar cell. For that we use AR coating texturing, means to increase the number of photons that actually affect the surface of the solar cell. So anti-reflection coating is required so that it should not go back. There should be absorbed, more and more should be absorbed. And texturing so that surface area is increased. And thickness of the absorber layer is also maximized so that more and more electrons are captured, photons are captured. So you see this inverted pyramids type structure and fingers like this have been used to enhance the efficiency. This is one more thing. When we talk about the flexible solar cells, so you know what happens. Okay. So if we see here, direct band gap of copper, indium, gallium diselenide allows incident light to absorb much faster than the silicon. So see that a silicon layer must be 10 raised to power 4 micrometer, means 10 millimeter thick to absorb 100% of light. On the other hand, copper, indium, gallium selenide needs only 2 micrometer thickness to achieve this speed. So that means optimum thickness of the film. What is optimum thickness? The thickness, that thickness by which you can absorb 100% of the incident light. So optimum thickness in direct band semiconductors is much lower than the indirect band semiconductors for photovoltaic effects. So silicon, if you are using, you need to have a thick absorber layer. If you are using materials like CIGS, perovskites, you need very thin layer because its absorption coefficient is very high. So see that how solar cell works. That's very important. We should understand the phenomena. Now you have a PN junction diode. When light falls from the valence band, electrons goes to the conduction band, and you know, electron is here in the p-type material, and in the n-type material you have this bound positive ions, so it will be attracted by them, and holes will be attracted by the negative ions on the p side. So what will happen? These holes will start accumulating here, this side on the n side, electrons and holes will be accumulated on the p side. So they generate some voltage at the two ends. So if we don't apply any contact between p and n, there will be a voltage here. And what do you do if you take a wire and connect P and N sides with each other? So what will happen? All accumulated carriers will go there, and you will get a highest current, what, no voltage. So see here, see here, suppose I take the diode, I shine the light, but I keep it isolated. The maximum voltage that will be created shall depend upon the area of the solar cell and the type of the solar cell. So that will provide me open circuit voltage. And if I short circuit the two ends, I will get the maximum current, that is known as short circuit current. So these are the two things you can see: short circuit current, JSC, rather short circuit current density, open circuit voltage, VOC. Now, if I put some resistance to that short circuit in place of short circuit, so I will get somewhat lesser current and somewhat positive voltage. So, and if I keep on changing that resistance, I will get this type of behavior, right? So this is how PN this diode works as a solar cell. Now, solar cell summary: light is absorbed and produces electron hole pairs. PN junction separate these because charges in the depletion region separate electron hole pairs, and these carriers are collected or accumulated at the two ends. Current flow in the external circuit produces a forward bias voltage, and forward bias diode current reduces the total current. So this is the power out is given by this, and three approaches. Now I earlier also talked about three objectives. Here three approaches are also there. Either I want high efficiency solar cells, means high cost solar cells and high quality crystalline materials. I am ready to pay high cost. I need high efficiency. So what will happen? I will use high quality crystalline materials for making the solar cells. Second approach, acceptable efficiency. That means uh, I want low cost. I am ready to compromise the efficiency. Then I will use thin film or amorphous polycrystalline material absorber layers. Third one is the concentration. High efficiency cells with optical concentration. So you must have seen in the table also, the highest one has been possible with concentration, optical concentration. So these are the three approaches which are kept in mind while developing the solar cells by the R&D people. And the solar cell efficiency limits, how to have a look on it. Fill factor. Fill factor is one aspect. Means the dark area that you see is known as fill factor. You find out a point so that this area is maximum. It is determined by the diode characteristics and series resistance. Short circuit current increases as the band gap decreases. If you choose low band gap materials, you can have higher short circuit. And for a given band gap, short circuit depends upon reactive reflection, absorption, and recombination. Open circuit voltage increases as the band gap increases, and for a given band gap determined by the recombination. So solar cell, if you join solar cell in series and parallel, you make module. If you take module and make it series parallel combination, you get the solar array. Now, if you talk about the technology of the solar cells, okay, I don't touch this. So these are the various techniques that are used for making the for achieving the solar cells: vapor phase deposition, chemical deposition. These are chemical process or physical process. They are very important. So in physical process we use vapor phase deposition. Chemical process we use liquid phase solution deposition. So you see, so many things are there, so many techniques are there. So let me introduce few of them. The very simple one, the physical vapor deposition. So what do? You you take the material, heat it up, and create its vapors, and take the substrate, and vapors are deposited on the substrate, and then you uh, use it. So vacuum coating unit used for thermal oblique flash evaporation of thin film depositions is facilitated with evaporation process, glow discharged, ion cleaning, substrate heating, flash evaporation, multi-source evaporation, and co-evaporation. And you get films like this, atom by atom, they are coming, sitting their places and forming the. And this is how this cross-sectional view looks like for MB and MOCVD. So I just want to take you 5 minutes more and show you some important results. So these are, there are, I told you CIGS. So what is CIGS? CIGS is a chalcopyrite. Because I am working on this, so I want to share it. Chalcopyrite is what? Chalcopyrite is a mineral and the most important ore of copper. It's a sulfide mineral consisting of copper, iron, and sulfur that crystallizes in tetragonal crystal system. So it is known chalcopyrite due to its chalcopyrite structure. So its molecular formulation is ABC square, or group 1, group 3, group 6, 2 atoms. A can be copper, is fixed. B is indium, gallium, or aluminium, any of these. C can be S, selenium and tellurium. So this is the structure. Here you can see that red copper, yellow selenium, blue indium gallium. So instead of yellow, in yellow, you can take sulfur, selenium or tellurium. So that means you using the same structure by making solid solutions with different atoms, you can have a band gap flexibility from 1 electron volt to 1.7 electron volt. If I use copper, indium, aluminium, selenite, I have just touched the third group, not touched anything else. And if I use copper, indium, gallium selenide, we can have band gap from 1.0 to 2.7. So you can see that by changing the band gap, a lot of properties are changed. We have already studied it, so this we can do. So this has already told that its thickness for 100% optimum film thickness is very low, so it is a flexible material. And see here, this is how we make CIGS solar cells. You take a glass substrate, or you can take soda lime glass, or you take polyamide matter foil. On that you use molybdenum layer back as a back contact. It reflects unabsorbed light back. So whatever light comes reach here is a reflected back. Then PIGS is grown by the methods I have shown you earlier. Then thin type CDS buffer layer is absorbed on that. Buffer layer is overlaid by intrinsic zinc oxide to protect CDS and absorber layer. So intrinsic zinc oxide is put here. It will not allow disturbance of CIGS and the CDS. And on that we put the window layer, which is zinc oxide aluminum doped. Aluminum doped zinc oxide layer acts as a window layer. So this is how we make the CIGS solar cell. You see that actual cell has been made in our lab also, and this is the picture, SAM picture, cross-sectional. And these are the different methods we can use. And this how we do, we make a stack of this, then we anneal, and finally we get the single phase. So this is absorber layer. On that we make window layer of indium sulfide, and then we make diodes, the Schottky diodes. You can see the ohmic contacts also we have tested. Then the diodes were fabricated, IV characteristics were measured, and finally this solar cell was also tested. And see, this is in the open sun. We tested the VOC and ISC, so they are there. And these are the facilities available in our lab. We have vacuum tube sealing setup. You can seal, you can fuse, you can make the material and then make it a powder of it, then deposit in the form of thin films. You have atomic layer deposition, we have thermal and flash evaporation setup. Then we anneal it to grow in a particular phase. Then we characterize X-ray diffractometer, this is the spectrophotometer, CV measurements, IV measurements, probing, and you can say CCD scope, you can see on the monitor, you can have automated characterizations. Then of course perovskites, which I won't touch because I have taken a lot of your time. So thank you very much. Any question please, or any comment?